All right, in the first chapter, we're going to learn a lot about what organic chemistry is, different types of organic molecules, what gives the molecules its properties, and we'll talk about more about being able to look at a molecule and trying to predict some properties of the molecule. And so looking at the structure. First of all, what is organic chemistry? Organic chemistry is basically the study of compounds that contain carbon. It's a little bit more than that. It's really carbon and hydrogen. All right, for example, carbon dioxide has a carbon, but this is not an organic molecule. All right, it really has to have at least a carbon and some hydrogens attached to it. All right, in particular, the most simplest organic molecule is CH4. This is called methane. We will look at this again in the next slide. Okay, so really organic chemistry is the study of compounds that have carbon and hydrogen on them. All right, now they will also have other atoms like oxygen, nitrogen, sulfur, some of the halogens, but pretty much you have to have at least carbon, hydrogen. Organic molecules are virtually in everything. It's part of everything in our lives: clothes, foods, medicines, gasoline, refrigerant, soaps. All right, everything that we come in contact with is somehow organic chemistry is involved. All right, and there are two sources of organic molecules. One is from natural sources, things that we get from our natural environment. Cotton, wool, silk, these are all examples. Aspirin is actually an example of one that that was found. Actually, a lot of drugs are actually found in our natural environment, um, and however, we don't isolate all of it out of the natural environment. We have to synthesize these compounds. So because you can't go down chopping down all the trees that have aspirin in it, so you have to somehow find a way to synthesize it. So a synthetic molecule, in this case, they're trying to show you synthetic molecules that are not naturally in our environment, like nylon and polyester. Now, aspirin is an example where it's kind of a tie between these two. It's a compound that was found in a natural environment. However, we have to synthesize it in order to make large quantities of it. However, it's still considered a natural compound. But nylon, polyester, a lot of the sweeteners that we use are completely synthetic. There's a lot of compounds that are completely synthetic that are not found in our environment. All right. Some examples of organic molecules: methane, like I said, is CH4. So just to kind of go over some terminology, this is called the formula, the chemical formula or the molecular formula. You'll kind of use both terms used interchangeably. Chemical formula or molecular formula. This is the chemical structure, right? This is the structure, all right? We're going to look, the structure is much more important because it gives you some information about the molecule and you can kind of figure out some properties of the molecule. Okay. A second compound is ethanol, which is found in drinking alcohol. Okay, this is the structure for it, the chemical structure. The formula would be C2H6O. Usually when you write organic molecules, you always write the number of carbons first, then the number of hydrogens, then any other atoms you have after that. All right. Just to kind of give you a kind of a heads up and kind of a sneak peek at what we'll be seeing in the future, and you might be thinking about this, well, I can redraw this molecule a different way. So rather than having the oxygen on one of the outer atoms, you can have the oxygen in between the atoms. And notice the formula is still the same. This is still C2H6O. So this is why it's important to understand the structure, not just the formula, because notice these are the same formulas, but these are not the same molecules. Their properties are way different. This, you can put in alcoholic beverages and drink. This, if you drink, you would die. Okay, so that's why I find organic chemistry very interesting. By just little changes in the molecules, you have drastically different effects on a living organism. Okay, and these are what's called isomers, constitutional isomers, and I believe we'll learn about it in a later chapter. All right, here's another example. Here's a really big molecule. This is a natural occurring molecule found in our natural environment. This is called capsaicin. This is what you find it's what gives the spiciness in foods, all right, in a pepper. And it's also been used as a pain reliever because of the spiciness. It kind of absorbs into the skin and affects the nerve pathways by where the pain is, so it stops the impulse, like that nerve impulse of the pain. But you can see this is a very complicated structure. There's lots of carbons here. Okay, you can see all the carbons. You also have a double bond. This is called a double bond. You have a double bond to an oxygen. You have a nitrogen here. You have a ring compound, all right, with alternating double bonds. All right, this is called conjugation when you have a double bond, single bond, double bond, single bond, double bond, single bond, conjugation. Again, I'm throwing out terms that you don't need to know quite yet, but we will probably learn throughout the semester. Conjugation, not shuns, there we go. Okay, this is also what's called a benzene ring. All right, you might have seen in other books, benzene ring, they kind of do it like this without showing you all the carbons. We will talk about that in this chapter. So just to kind of give you a head start or a beginning of what we're going to start doing. So you can see that's a pretty complicated structure. All right, here's caffeine. Found in coffee, tea, in soda, in chocolate. Pretty much also a natural compound. You can see there are 2 rings. There's a 6-membered ring here, and there's a 5-membered ring around here, 2 double bond oxygens, nitrogens, carbons and hydrogens. So these are just really good examples of organic molecules that are kind of in everyday life. I don't think capsaicin's in your everyday life, but caffeine definitely is. Okay, so like I said, all organic compounds contain carbon and a hydrogen atom. All right, and this is just to kind of show you a Lewis structure, if you remember from Gen Chem. So I'm going to be using a lot of Gen Chem terms that you are required to remember, like what a Lewis structure is. If you don't, please review. We definitely will talk about it in class more. But remember, everything has to be an octet. So your carbon has to have an octet, has to have 8 electrons around it. And it has these 2 here, these 2, these 2, these 2, and these 2 for a total of 8. And since the hydrogen is sharing them, this bond is called a covalent bond, okay, because they are sharing the electrons. Most bonding we're going to talk about in this semester is covalent. Ionic, remember, is the other type of bonding. That's like if you have a metal attached to a non-metal. You have ionic bonding. Sodium has a plus charge, chlorine has a minus charge. That's ionic bonding. Okay, that's with a metal and a non-metal. We're not really going to be talking too much about that. Mostly on the period, so if you look at the periodic table, this is kind of a quick show of a periodic table. If you guys remember that line, that staircase line, on the right side, remember, are the non-metals, and everything to the left of it are the metals. Hydrogen is kind of a weird one. All right, we're pretty much going to be dealing with everything in this range right here, plus hydrogen. Okay, this is where our world is for this semester. Carbon, hydrogen, nitrogen, oxygen, sulfur, the halogens. You guys remember what the halogens were? The halogens are our 7A row. So fluorine, chlorine, bromine, iodine. Okay, these are the major atoms that we're going to be dealing with. It's funny because a lot of people say organic chemistry is so hard. Well, it's really just about 5 atoms. I mean, come on, how hard could it be, right? Just to kind of give you an idea, we're not going to be talking too much about metals at all. Okay, so to go back, covalent bonding, sharing 2 electrons. So every time you see a bond, that's 2 electrons. So there's 2 here, 2 here, 2 here, 2 here. 1 atom comes from the central atom. I'm sorry, 1 electron comes from the central. The other electron comes from the outer atom. Okay, so didn't know there's other information here, so let me erase this. Carbon always makes 4 bonds. Okay, carbon always makes 4 bonds. This is a rule or a law that you need to memorize. Always 4. And it can be a combination of single bonds, double bonds, or triple bonds, but it's got to be 4. Okay, the reason is because if you look at the Lewis dot structure, if you remember the Lewis dot structures, carbon is in the 4A row of the periodic table. Okay, your book doesn't talk too much about this, but I think it's important to kind of know because it kind of ties together what you learned last time in Gen Chem. So 1, 2, 3, 4, 5, 6. Carbon is right here. This is where carbon is. This is the 4A. You guys remember the 1A, the 2A, the 3A, 4A, 5A, 6A, 7A, You might have learned in your Gen Chem that everything in the 1As have a +1 charge. These will have +2 charges. 3As have 3 plus charges. And then we kind of skip the 4s. We say, well, 4s, there's kind of, you can have plus or minus, so let's not worry about it unless you take organic. Well, now you're an organic, so we kind of have to worry about it now. So carbon is 4, so if you do the Lewis dot structure, 1, 2, 3, 4, that's your 4 valence electrons, but carbon needs 8. So you need to fill up these 8 other spots. That means carbon needs 4 more electrons, or 4 more bonds. So that's why carbon always makes 4 bonds. Okay? And hydrogen atoms always make 1 covalent bond. All right, remember hydrogen has 1 electron. Hydrogen is fine with only 2 electrons. Remember, it's called a duet rule. With carbon, it's called an octet rule. I don't know if you've learned this term duet, but that's kind of what they say for hydrogen. Hydrogen's special. Hydrogen only wants 1 bond. Every other atom, carbon, nitrogen, oxygen, the halogens, sulfur, these all want, halogens, these all want an octet. Okay, and I believe there's a slide that will show this, but for right now, let's show you how carbon can have more than a single bond. So like I said, single, double, triple. So here's a case where carbon has a single bond. Here's the case where carbon has a double bond. Notice this carbon still has 4 bonds. 1 here, 1 here, 1 here, and 1 there for 4. And this carbon has 4. Same thing for the triple bond case. This carbon has 4 bonds. 1 here, and then 3 in the middle for a triple bond. And notice your hydrogens always have a single bond. All right, you obviously can't do a triple bond onto hydrogen. That won't work. Carbon could do a triple bond, but hydrogen cannot do a triple bond. So don't do things like this. Okay. Also, just to kind of give you an idea of other types of shapes, is that carbon could be either what's called a chain, a straight chain, or it could be a ring. You can put them in rings. Okay, so here's an example where you have 3 carbons that's in a straight chain. Here's an example of 3 carbons that's in a ring. All right, you'll see lots of rings, especially 5-membered ring and 6-member rings are very common. Okay, organic compounds may also contain elements other than carbon. All right, these are called heteroatoms. This is the oxygen, nitrogen, sulfur, halogens. These are atoms other than hydrogen and other carbons. Okay, each heteroatom forms a characteristic number of bonds determined by where they are in the octet rule, but remember you still have to have a total of octet. So here's your nitrogen, oxygen, halogens. They don't have sulfur in here, but sulfur is kind of one that we'll see a little bit. All right, so this is kind of a good chart. I like this chart a lot because it really is a summary of all this, and it shows you how these atoms have to bond. Okay, hydrogen always has 1 bond with 0 lone pairs. Okay, carbon has 4 bonds, period, makes 4 bonds, and it could be in the form, it could also be a double and a single, or it could be a triple and a single. Nitrogen is in the 5A row on our periodic table, so if you do the Lewis dot structure, 1, 2, 3, 4, 5 valence electrons, notice this is paired up. So nitrogen has 3 more spots in order to become an octet. So nitrogen only makes 3 bonds with a lone pair. So here's your 3 bonds, lone pair. Same thing, you can have all singles, you can have a double and a single, or you can have a triple. All right, oxygen is in the 6A row. So 1, 2, 3, 4, 5, 6 valence electrons. It has 2 remaining spots. So that's why oxygen always makes 2 bonds. 2 bonds and 2 lone pairs for a total of 8. So oxygen can either be singles with 2 lone pairs, or it can be a double with 2 lone pairs. And then finally, halogens is in the 7A. So 1, 2, 3, 4, 5, 6, 7. X is kind of a universal symbol for halogens. All right, so it's got 1 spot available. So halogen can only form 1 bond. It cannot form a double bond or anything like that. Halogens just basically 1 bond. Okay, you need to memorize this. This has to be so ingrained in your system that it's just automatic. When you start drawing molecules, I don't want you to have to think about it anymore. I don't want you to think about, okay, how many bonds does oxygen make? Well, it's valence electrons of 6, therefore it needs 2 more. You should just know oxygen can make 2 bonds, either 2 singles or 2 doubles. All right? Okay, and this we've already talked about. This just says oxygen can either make single bonds or double bonds. All right, and we're gonna stop right here for the first video, and when we come back, we will start with 11.3.